Okay, here is a solution for question 2 of our conservation of energy problem. So we have a rod, and it's free to rotate about its base, and it starts in a vertical position and it falls clockwise until it hits the ground. So how are we going to solve this problem? Well, the best way to do this is using conservation of energy. So we want to look at our total mechanical energy initially when the rod is straight up, and that should equal the total mechanical energy when it hits the ground, or just the moment it hits the ground. So let's look at the left-hand side. We have the initial energy is just the sum of our kinetic and potential energy. Well, in fact, our final energy is the same. It's K final plus U final. Well, initially this rod is at rest, so the kinetic energy is 0. So we just have potential energy. And in our final position, all of our potential energy gets converted to kinetic energy. So our final potential energy is 0. So that just leaves our initial potential energy here equaling our final kinetic energy. So our initial potential energy, we're going to use the center of mass. The center of mass is the middle of this rod. And we can write the potential energy is just the, it's m times g times the height, well, it's the distance the center of mass is off the, above the ground. So that's just mgh. Oops. Now, our final kinetic energy. Well, this rod is going to rotate, so we're going to have rotational kinetic energy, and it's given by the equation 1/2 times the moment of inertia times the angular velocity squared. Okay, so first thing, a rod rotating about its one end has a moment of inertia given by 1/3 times its mass times its length squared. And also we know that the angular velocity, omega, is related to the tangential velocity divided by the radius, or in this case the length of our rod. So this is the angular velocity of our rod as it falls. So let's work with what this equation we have. We have m times g times the height. The height is just half the length. This is equal to 1/2 times the moment of inertia, which is 1/3, times the mass times the length squared, times omega squared, which is just v over L squared. There. So if we look at this, our L squares cancel, and this half here cancels with this half, and then I can, well actually, I have two symbols for mass here. Sorry, those are actually the same. So little m here is equal to big M, and they're going to cancel. And when all that's left to do is solve for the speed, which is the square root of, this should be squared here, 3g times L. So then we just plug in our numbers. We have 3, g is our 9.8 meters per second squared, and L is the length of the rod, which is 3 meters. And hopefully I've done this right, and I computed this to be 9.4 meters per second.